NVIDIA NCA-AIIO exam practice questions with explanations are available in the video for you to study. A medical research organization plans to integrate AI systems to assist with early disease detection using radiology scans. The team wants to understand the main reason AI systems have recently become powerful enough for such tasks. Which of the following has been the most significant enabler for scalable image recognition with AI? A. Breakthroughs in GPU processing power that allow massive parallel computation on large datasets. B. Introduction of specialized AI programming languages. C. Greater access to diverse medical imaging datasets for training. D. Declining costs of data storage, enabling larger archives of training data. The answer is A. The main catalyst for modern AI's success is hardware acceleration, especially GPUs that perform parallelized matrix computations essential for deep learning. These advances allow neural networks to process vast datasets efficiently. While data availability and storage costs matter, they are secondary factors. The true scalability comes from computational improvements. Without powerful GPUs, training and inference at today's scale would not be feasible. When designing infrastructure for distributed deep learning training, which networking capability is most vital for maintaining performance and scalability? A. Establishing redundant network paths to avoid downtime. B. Segmenting networks to isolate specific workloads. C. Ensuring ultra-high bandwidth and minimal latency between GPU servers. D. Using wireless connectivity for flexible deployment of compute nodes. The answer is C. Deep learning training often involves large data exchanges between GPUs and nodes, making bandwidth and latency crucial. High-speed interconnects like InfiniBand reduce communication overhead. Redundancy and segmentation are secondary operational concerns. Wi-Fi lacks the stability and throughput needed. Efficient networking directly translates to faster model convergence. An AI operations team notices uneven GPU utilization across servers in their data center. Some are idle while others are overloaded. Which approach best optimizes workload distribution automatically? A. Deploy NVIDIA GPU operator integrated with Kubernetes for dynamic GPU scheduling. B. Add more GPU servers through horizontal scaling. C. Manually move workloads based on current utilization metrics. D. Upgrade cooling infrastructure to improve thermal efficiency. The answer is A. The NVIDIA GPU operator works with Kubernetes to automate GPU scheduling and monitoring. It dynamically allocates workloads to available resources, improving utilization. Manual or hardware-based approaches cannot scale efficiently. Adding servers won't fix imbalance, it would worsen it. Intelligent orchestration ensures balanced performance and higher efficiency. You are deploying a fraud detection system that must adapt continuously as new transaction patterns emerge. To maintain accuracy over time, what strategy should be implemented? A. Set up a continuous retraining process that feeds the model with live data streams. B. Operate the AI alongside traditional rule-based systems for reliability. C. Retrain only when performance metrics drop below a threshold. D. Use a static dataset and retrain the model periodically. The answer is A. Streaming retraining enables models to evolve as data patterns shift, preventing concept drift. Fraud detection environments change rapidly, so static retraining cycles are inadequate. Continuous learning ensures the model adapts to new fraud types. Hybrid or delayed retraining may cause accuracy lag. Real-time pipelines maintain responsiveness and trustworthiness. An AI team must deploy a 24/7 inference service that balances performance, uptime, and energy consumption. What is the most effective strategy? A. Run inference tasks in scheduled batches during low-demand periods. B. Use auto-scaling GPU clusters that activate or deactivate GPUs based on real-time load. C. Keep a constant number of GPUs running at half capacity. D. Operate a single high-performance GPU continuously at full utilization. The answer is B. Auto-scaling dynamically matches GPU usage to workload demands, optimizing both energy and availability. Batch processing compromises real-time performance. Fixed capacity clusters waste power during low activity. Single GPU setups lack resilience. Adaptive scaling is the best practice for sustainable AI inference operations. In a Kubernetes-based AI inference environment, some GPU nodes are overworked while others remain idle. Which solution ensures balanced workload distribution across all GPU resources? A. Implement a GPU-aware scheduler within Kubernetes. B. Reduce the total number of GPU-enabled nodes. C. Apply GPU usage quotas per pod. D. Use CPU autoscaling to distribute workloads. The answer is A. GPU-aware scheduling allows Kubernetes to intelligently assign workloads to available GPU resources. It eliminates imbalance by tracking GPU allocation at runtime. Reducing nodes or enforcing quotas doesn't improve distribution efficiency. CPU autoscaling doesn't account for GPU utilization. Smart scheduling optimizes inference throughput across the cluster. A researcher is studying how dataset size and hyperparameter tuning affect model overfitting and generalization. Which analytical approach best identifies relationships between these factors? A. Analyze accuracy progression over epochs using time series methods. B. Use a decision tree analysis to map how dataset and hyperparameters influence overfitting risk. C. Plot training and validation accuracy on a scatter graph. D. Build a histogram showing overfitting occurrences by dataset. The answer is B. Decision tree analysis helps visualize causal relationships and variable interactions. It allows researchers to see which factors contribute most to overfitting. Scatter plots and histograms show trends but lack interpretability. Time series analysis only tracks temporal patterns. Decision trees provide structured insights into performance determinants. In a distributed training environment where jobs have dependencies and varying priorities, which orchestration model best ensures optimal scheduling and execution? A. Round-robin job assignment. B. FIFO, first in first out, queue processing. C. Directed acyclic graph, DAG, based workflow orchestration. D. Manual job coordination by administrators. The answer is C. DAG-based orchestration models complex workflows efficiently by defining task dependencies and execution order. This approach ensures resources are allocated in sequence with job readiness. FIFO and round-robin lack dependency awareness. Manual scheduling is error-prone and inefficient. DAG orchestration tools like Airflow or Kubeflow are industry standards for large-scale AI training. While training a deep learning model across several NVIDIA GPUs, a data scientist observes slower than expected performance. Which issue is most likely causing the bottleneck? A. The GPU memory is overloaded due to an oversized batch size. B. The model architecture contains too many layers. C. The learning rate parameter is too small. D. The dataset is not being distributed, sharded, efficiently across GPUs. The answer is D. Improper data sharding leads to uneven workload distribution and idled GPU cycles. Each GPU must process a balanced subset of data for efficient parallel training. Batch size, architecture complexity, and learning rate affect convergence but not inter-GPU efficiency. Correct data parallelism ensures full hardware utilization. Optimized sharding significantly accelerates training throughput. In a shared GPU cluster where several users run simultaneous training jobs, one user reports poor performance despite adequate GPU allocation. Storage I/O appears saturated. What is the most likely root cause? A. GPU memory is insufficient. B. Data loading from storage is inefficient, creating a bottleneck. C. An incompatible CUDA version was installed. D. CPUs are oversubscribed. The answer is B. High storage I/O indicates a data throughput issue during training. Slow data loading prevents GPUs from receiving data quickly enough, causing underutilization. CUDA or CPU issues would manifest differently. Efficient data pipelines, such as caching or prefetching, are crucial for maximizing GPU performance. Optimizing I/O is essential in multi-user AI environments.